Exponential functions you should remember from Algebra 1. Okay, if that's not the case, we're going to really look at them pretty well here. So I want to compare the two functions, f of x and g of x, based on the information in the table. Okay, x is going to be the same for both functions. X is these numbers in the far left column. Okay, this set of numbers, 0 through 6. In f of x, it is 2 to the x power. 2 to the x power. So if I raise 2 to the 0 power, I output 1. If I raise 2 to the first power, what do I output? 2. So far, this function and this function look exactly the same when x is 1. Can you see that? But what if I raise 2 to the second power? Oh, so it's 4 and this one's 4. Okay, so far there's not much difference there. What if I raise 2 to the third power? 1 is 8 and 1 is 6. Okay. What if I raise 2 to the fourth power? 16 and 1's 8. 2 to the fifth? 32, while 2 times 5 is only 10. Okay, so what happened is on the right side here, this set of numbers, this is linear. Y equals 2 times x. What that's going to look like is some kind of line. It's growing. It's increasing. Okay, it's increasing at a rate of 2 per x value. But on the left, this is y equals 2 to the x power. And so they're going to look a little bit the same for a minute. And then all of a sudden, the 2 to the x power is faster. It rises much faster than the other. If you look at the comparison, 2 to the fifth is 32. 2 times 5 is only 10. So it doesn't take us very far out in x before all of a sudden the exponential one is much higher than the linear one. Can you see that? They both tend to go to infinity. If I was writing the limit statement here, I could say this is the limit as x approaches positive infinity of f of x. And for both of them, they go up. So for both of them, the limit would be infinity. However, the exponential one goes much faster. Can you see that by the table values? Okay, good deal. So a lot of what we're talking about first is just conversation. It says exponential growth refers to the original value from the range increases by the same percentage over equal increments, versus linear growth increases by the same amount. Okay, so is it going to add the same stuff or is it going to multiply every time? If it's multiplying by the same number every time, it's exponential. Look back at this table. What are they multiplying every time by to get to the next number? 2, right? 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. Can you see it? It's a factor of 2 every time. Versus on this table, what are they doing? Adding 2. So linear growth is going to change by the same addition or subtraction every time. Exponential growth is going to multiply every time. Can you see the difference? Yeah? Okay. One thing you should know is if b is greater than 1, we're dealing with growth. Growth, those functions go up from left to right. They're increasing. If b is between 0 and 1, we're dealing with decay. Those functions decrease from left to right. Decay, decrease. Okay. What's a number between 0 and 1? 0.5, a decimal, or a fraction. Okay, a decimal or a fraction. All right, so here's an example of this function again, but actually graphed on paper. Okay, so it's the same table of values. We've got x is -3, -2, -1, 0, 1, 2, and 3. And we're inputting into the function f of x equals 2 to the x. Remember that when I raise something to a negative power, okay, when I raise something to a negative power, this 2 to the -3 power could have been written as 1 over 2 cubed. Do y'all remember that when my exponents are negative, we can send them to the bottom and make them happy? 2 to the 2 is 2. 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 2 to the Do you remember learning that when we did properties of exponents? If it's negative in the top, I can throw it in the bottom and it'll be happy. So this one is 2 to the negative 2 power. Can y'all see that? That comes out as 1 over 2 squared. 1 over 2 squared, and that's going to be our fourth. That's where these fractions are coming in. Okay, so if you're having a negative exponent, it comes out as a fractional output, which makes sense. As we move to the left, you can see that these numbers are getting smaller and smaller and smaller on this particular function. When we raise to a negative power, we output fractions. And the fractions are decreasing as we go to the left. Can you see it? Okay. If I brought in a donut to this class and I divided it by 2, and I gave Shub half, okay, because I like Shub the most, that's why I gave him half. And then I divided what was remaining by half again, and I gave half of the half to Joseph, because I like him second best, so he got a quarter of the donut, right? And then I divided what was left of that quarter in half. Who gets it next? Probably Dana. Dana would get an eighth of the donut, right? And I would keep doing that as long as I had donut. Would I ever actually run out? No, because I could divide that donut almost down to an anatomical level, right? But how much donut is each person getting? Not very much. By the time we get down to Marcus, y'all are listening. By the time we get down to Marcus don't have. No, Marcus is definitely last. No, I'm so glad you came to school today, Marcus. By the time we get down to the very end, even Marcus gets a crumb. Okay? There's not ever going to be no donut. As long as there ever was donut, there will always be some donut. Do you hear me? As long as there ever was donut, there will always be some donut. So the way this works is it has what we call a horizontal asymptote. Is that your question?
Yeah, I was thinking about that.
Good, Wyatt. So it has a horizontal asymptote on the line y equals 0. We never actually go into negative land. We may be very, very, very small, but it's not going to be 0. As long as there ever was donut, there will always be some donut. You will never have negative donut. Are we clear? Okay, so that brings us to this. It says, let's define the behavior of the graph. Well, the domain is negative infinity to positive infinity. This thing goes forever and ever left and forever and ever right. You can see that when you look at the picture. You can tell it's going up, but as it's going up on the right, it's also getting wider. You could input a big number in x. Okay, it's not defined by, I've only got 6 values here. You could go to infinity in x. So your domain is all real numbers. The range, though, goes from 0 to infinity because I'm not ever going to have less than 0. Are you with me on that? So even as far negative as it goes, it's just going to ride out on 0 to the left. As x approaches infinity, f of x approaches infinity. As x approaches negative infinity, f of x approaches 0. That's that asymptote. Okay. F of x is always increasing. That's because our B number here, 2, is greater than 1. As long as 2 is greater than 1, we're going to get bigger. That's growth. The graph of f of x will never touch the x-axis. We just talked about that. So y equals 0 is the horizontal asymptote. It also crosses the the y-axis. And this is important. It crosses the y-axis at 0, 1. That is because anything raised to the 0 power is 1. I lost y'all. Y'all went back to sleep. I was giving you like the good bullet points, and all of a sudden I lost you. Anything raised to the 0 power is 1. Okay? Anything. 8 to the 0 power is 1. k to the 0 power is 1. Your shoe to the 0 power is 1. Okay, so you can see that unless there's an a term in front of the b term right here, unless there's an a term, it's going to cross through 0, 1. Okay, so this is the information that you should have had on your paper, and this is going to be about 10 minutes in. So those of you that did not get this written down on Friday, you want to go on the YouTube video, find this stamp at about 10 minutes. Put that on your notes. At 10 minutes, these are where your notes are. Okay. And it goes over the actual, just the parent function, the toolkit function. This isn't looking at if I've got a 2 in B spot or any actually specific function. These are just general rules for exponentials. I will say that you can see that A is a non-real zero number called the initial value. A is the initial value. Another thing you might want to write on your notes is A is going to be the y-intercept. A is the y-intercept. It's called the initial value because it's the starting point. It's the y-intercept. Let's look at y. Why does A work out to be the y-intercept? Where am I located when I'm on the y-axis? X equals 0, right? So what if I take this function f of x equals a times b to the x, and we evaluate for f of 0? F of 0 equals a times b to the 0 power. What is b to the 0 power? 1. Can you see it? That's why a is the y-intercept, because f of 0 is a every time. It's like putting in 0 for x and y equals mx plus b. What do you get? When you put 0 for x and y equals mx plus b, what do you get? B. B. That's why b is the y-intercept. This is why a is the y-intercept, the way that they work out in the functions. Are y'all following this? Yeah? You got to perk up a little bit. I told you I'm going to cram it down your throats today. The range of f is all positive numbers if a is greater than 0. What that means is it's going to be located above the x-axis. If a happens to be less than 0, what do you expect to happen? That number in front, a, is less than 0. What kind of number is less than 0? A negative number, right? Well, what do you expect to happen to the function if I put a negative number in front? It's going to flip. So in that case, your range is going to be everything less than 0. It'll flip right under the x-axis. Can you see it? Yes? Wake up. Wake up. Everybody show me your 10 fingers. You got 10 fingers? Wiggle them. Something. All right, look at example 1. Example 1 says, identifying exponential functions. Which of the following is not exponential? So for it to be exponential, it depends on where x is. Okay? X must be in the exponent position. If x is in the base, it's polynomial. We've learned about all polynomial functions this year. We had x squared, those are quadratic. We had x cubed, those are cubic, right? We even dealt with quartic functions, x to the 4th plus 3x squared plus 2. That's something polynomial. You know it's polynomial because x is in the basement. It's down. These are exponential because x is in the attic. It's in the exponent position. You with me? So look at these 4 options. Which of the 4 is not an exponential function? G. G is polynomial. Okay. Any questions on that? We're looking at the location of x. It's up, 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 down. Not exponential. Okay. All right. Example 2 says evaluate f of 2 without using a calculator. When we see the word evaluate, it typically means we're going to plug in. Okay, when we see evaluate, it typically means we're going to be plugging in. So I would write this function down. This is f of x equals, this is example 2. F of x equals 5 times 3 to the x plus 1 power. First of all, what's your initial value? 5. Good. Way to go, Marcus. You're earning more donut. A is 5. Because that's the number in front. You with me? Okay. Is it growth or decay? Growth. Why, Joseph? Because B, not because it's positive, but because that B number, 3, is greater than 1. If B was a decimal, it would be decay. Can you tell that 3 is more than 1? So it's growth. Yeah? No questions so far? Our job on this particular example, say, evaluate f of 2. Evaluate f of 2, meaning plug in 2 or substitute 2 and see what happens. What is 2 plus 1? 3. So we're going to have 5 times 3 cubed, or 3 to the third power. Anybody off the top of your head got 3 to the third? 27. Benedict, you got 5 times 27? 235. I knew I could count on you. F of 2 equals 235. Is that right? Okay. You're amazing. You can stay. It's 135. He's sleeping. What are you doing over there? You know weekend numbers. Not over here. You're my human calculator. 135. Are we good with this? Evaluate? Not so hard? Do we want to do the try it, or are we good to move on? We can plug in a number. We're okay? Huh? We got it. All right, moving on. Example 3. Example 3, it says at the beginning of this section, we learned that the population of India was about 1.25 billion in the year 2013, with an annual growth rate of about 1.2%. The situation is represented by the growth function, P of t equals 1.25 times 1.012 to the t power, where t is the number of years since 2013. I want to look at a couple of things here. Okay. This function, P of t, represents the population growth in India. 1.25 represents what? The number of people initially when we started the clock in the year 2013. Okay, so we're talking about this function, P of t. We know that 1.25 is the initial amount. It's the amount of people when the time started at 2013. We also see that it is growing at a rate of 1.2%. But in the function, what I see is 1.012. So I'm not real sure how I got from 1.2% to this 1.012. We don't know? We don't know? Okay, so I used to teach this in 8th grade math. When they give me a percentage of increase, we have to do 1 plus r, where r is the percentage as a decimal. So they give you that percentage. They say, hey, it's increasing at 1.2%. We need to turn that into a decimal. Y'all remember this? And then we add it to 1 to stick it in the function. So it grows. So we would have 1 plus 0.012 or 1.012. And that's the number that gets to come in here as our growth rate. Are y'all feeling like this making more sense? Yeah. If it's growing, you have 1 plus the percentage as a decimal. Yeah. So the percentage as a decimal, 1.2, that becomes 0.012. You add it to 1 to show growth. You take it away from 1 to show decay.
So like negative?
It wouldn't be negative. It would be a decimal. So I would have 1 minus. Let's say I had 5% growth or 5% decay. Okay, convert it to a decimal. Yeah. So 0.05. Now take it off of 1.
So
1 minus 0.05. 0.95 would be your rate. So growth is going to be 1 plus the percent. Decay is going to be 1 minus the percent. Okay? You show them, see how it's 0.95? That shows decay because it's between 0 and 1. It's not ever going to be negative. If it's a decimal, it's going to be getting smaller. If it's a whole number or greater than 1, it'll be growing. Okay, so that's a little mini lesson on that piece of information. T is what here? Time. Number of years since 2013. We are supposed to find the population of India in 2031, which makes T be 18. Yeah. Number of years since 2013. So on your calculator, get after it. On your calculator, we're plugging in an 18 for T here. 1.25 times 1.012 to the 18th power. I did too. 1.549. Perfect. This is P of 18. Are we good here? No questions at all?
So that's the final?
Yeah, so that's the population of India. And this would be in billions. So 1.549 billion people. Cool? Let's try another one. This says in 2006, 80 deer were introduced into a wildlife refuge. By 2012, the population had grown to 180 deer. The population was growing exponentially. Write an exponential function n of t representing the population n of deer over time. Okay? Write an exponential function. So we know that in 0 years, t equals 0, there were 80 deer. So I would write down that ordered pair. 0, 80. That's our initial value. You with me? We also know that by 2012, which is how many years later? By 6 years later, there are 180 deer. So we know it's growth. We don't know what B is. What's the rate increase for B? How do you know that?
What is it?
He said he divided 180 by 80. Let me help you out. We know that A is 80, right? We're going to solve for B. Let's solve for B. We know that we're going to have n of t equal to A times B to the t power. Y'all with me on that? N of t, let's use this point for x and y, or for t and n of t. 6 is going to be t, 180 is going to be n of t. And we can work backwards here and solve for b. What is A? So 180 equals 80 times b to the 6th power. If you're not taking notes, you should be. I'd shut her down. Flip it over. Shut it. Bro. 180 divided by 80? Okay, let's call that 9/4. Equals b to the 6th. If it had just been a 1-year increase, what you did would have found b. But you weren't over consecutive intervals. Does that make sense? We jumped from 0 to 6. If we had jumped from 0 to 1, you could have just divided and found b. How do we solve for b? We've got b to the 6th power. How do I undo something to a power of 6? Not square root. The 6th root. So the way we show that is we raise it to the 1/6 power. So we're going to raise that 9/4 to the 1/6 power. That'll cancel the 6th. So on your calculator, 9/4 to the 1/6 power. 1.14, let's go 1.145. So now we can write our n of t. What was A? 80. And B? To the t power. There's our function. We need to walk back through how we got that, or you want to just work on the try it?
Try it.
Okay. We've got a wolf population growing exponentially. It says in 2011, 129 wolves were counted. So we've got 0,129. By 2013, the population had reached 236 wolves. So what's my other point?
Oh,
Anybody? 2,236. We want to use these 2 points. So that's what 2 points can be used. That's the first part of here, is write down the 2 points. Secondly, write the equation. So we're going to have n of t is equal to, how many wolves initially? 129 times b to the what power? To the t power. But now if I want to use this equation, we're going to put a 2 for t. Put a 2 for t. And instead of n of t, what number do I want to use over here? 236. And that's going to end up giving us a number for b so that we can write a function. Okay, so what's my first move to solve for b? Divide by 129. You got 1 point something? 1.829. Is b squared? So how do I get that by itself? Square root it? Oh, did you already square root?
Oh, no.
Square root it?
Do you want to do the whole number for accuracy?
3 decimal places.
Oh,
1.353. That is our b number. Huh?
Why would it be 2?
What b2?
352. Because the number after it's 40.
Was it already a 3? Or is it a 2?
35241.
Oh, it's a 2. I just didn't hear you right. Cool. Any questions on this one? Or on anything we did here? This is pretty nice. When they give you an initial value, this is how we do. Okay, when they go ahead and give you the A and the B, or they don't give you B, but they give you A. They give you a 0, comma something. This is how it works. When they don't, then we have to work a little differently here. So this is example 5. It says writing an exponential model when the initial value is not known. When the initial value is not known. And if you look at these 2 points, do you see them? -2, 6, and 2, 1. Can you see that? Yeah? The problem here is I don't have any of the points that have a 0 for x. So I can't use either one of them for our initial value. Okay, so somebody remember these 2 points. One is -2, 6. What's the other one?
2, 1.
2, 1. This is how we do this when I don't get the initial value. This is going to be example 5. How I work when I don't get the initial value. Negative 2, 6, and 2, 1. We're going to write 2 equations here. We're going to write 2 equations, both of them in the form of y equals a times b to the x power. For the first point, 6 is y. 6 is equal to a times b to the negative 2 power. You seeing what I'm saying here? For the second equation, 1 is equal to a times b squared. Cool beans? At this point, we have 2 equations. One of the free response questions for pre-cal that I'm teaching this year is this particular kind of question. They have to be able to write 2 equations, and they have to be able to solve for the right function. So this is great practice for you guys. We're going to take one of the equations, we're going to solve for a. I would say it's best to solve with positive exponents. That always feels easiest for me. Are you with me? So what we're going to do is we're going to take this second equation right here, 1 equals a times b to the second power, and we're going to divide both sides by b to the second power. So that we have a is equal to 1 over b squared. Cool? Once we have the number for a, we are going to go into the other equation with that information. So we're only down to one variable. So then 6 is going to equal 1 over b squared times b to the negative 2 power. Can you see it? Okay. I think that it would be really nice if we could make them both be on the bottom or both be on the top. I don't care which way we go with that. But somehow we want both of our b places to be in the same place, either both in the denominator or both in the numerator. Both in the denominator? Okay. So 6 is going to equal 1 over b squared times, how do I call b to the negative 2 if I'm going to write it in the denominator? Also 1 over b squared. Right? So this is 6 equals 1 over b to the 4th. How do I cancel that b to the 4th? Raise it to the 4th power or to the 4th root. We're going to have to raise it to the negative 4th root because what we're looking for is in the denominator. So if we raise this to the negative 1/4, we can cancel the b to the 4th in the denominator. Do the same to both sides. 6 to the negative 1/4 power. On your calculator, 6 to the negative 1/4 power. .639. Okay, so there's our b value. Now what do we do with that? Plug it back in to find a. We know that 1 over b squared equals a. So we're going to have 1 over 0.639 squared. Good thing Marcus is here. Marcus, you might get 2 donuts. This is just insane. Nobody else has their calculator out today. 1 over 0.639 squared. What'd you get?
2.44.
Perfect. 2.449 equals A. So what's our equation here? Times 0.639 to the x power. This is our f of x equals. F of x equals 2.449 times 0.639 to the x power. Okay. We're going to do one more. The try it that's just like this, and then we'll call it a day. Okay. So a try it gives us 2.13 and 2 comma 4.5. Do you want me to do it with you?
Yeah, edit this one.
Okay. Our 2 points are 1 comma 3, 1 comma 3, and 2 comma 4.5. Remember, the first thing we have to do is write two equations. We're writing them in the form of f of x equals a times b to the x. So what's my first equation?
Why?
Well, y is f of x. Same thing. 3 equals
A times B to 1 power.
to the first power. Okay. And our second equation?
4.5 equals A times B to the second power.
Perfect. Are y'all with me? So far, so good? Okay, now we want to solve one of them for a. Yeah, I think this first one's the easiest one because we're just going to divide by b on both sides. So 3 divided by b is a. Now, what do we do with that? Plug into the other one in place of a, 3 over b times b squared. And what happens with the b's? One cancels. I can lose this one and the fact that the top one was squared. So we have 4.5 equals 3b. Divide by 3 on both sides. We're solving for b. So 4.5 divided by 3 is 1.5. 1.5 equals b. Now what? Plug it back in over here so we can get a by itself. 3 divided by 1.5. 2. 2 equals a. So what is our function?
2 times 1.5.
F of x
To the
equals
power of
2
x.
times 1.5 to the x power.
Perfect. Perfect. Smooth job, y'all. Tomorrow we'll come in and figure out how to do that on the calculator. We have one more example, and then we'll start the second lesson. Okay, so expect us to have a mini lesson to finish this one, and then we'll also start 6.2. If you wanted to get going on your homework tonight, that would be a great idea.